All right, so it looks like we have a critical mass here anyway. So welcome everybody. It's 8 p.m. GMT, and we are in our fourth event of webinar series related to vector symbolic architectures and hyperdimensional computing. My name is Evgeny Osipov. So a small announcement. So we will run two more webinars. The next one will happen on 13th of July, and the last will happen on July 27th. After that, we will make a break until September and resume then. So, and I have one available slot on July 27th. So if anybody is interested to present, so please contact me. But now we have two interesting talks, and one given by Graham Bent and another one given by Alex Kelly. So without any due delay, so I leave the floor to Graham Bent. So please feel free to introduce yourself and start your talk. And I'm muting myself.
Okay, thanks very much, Evgeny. Yes, so my name is Graham Bent. I'm a contractor working for IBM Research in the UK. My co-presenter this evening is Chris Simpkin. Chris will be in the background to answer any deep technical questions that I struggle with. You can see here's the co-authors, and the title of our talk this evening is Dynamic Distributed Orchestration of Node-RED IoT Workflows using a vector symbolic architecture. Now,
sound is gone, Graham.
It's on. Okay, it muted me again for some reason. Okay. Right, so the work that we're presenting has been undertaken as part of a large collaborative research project, which is called the Distributed Analytics and Information Science International Technology Alliance, or DAIS-ITA for short. Now, DAIS is an alliance of UK and US government, industrial and academic researchers, and we're tasked with developing the basic science to underpin distributed analytics and information services, and to enhance the capability to conduct future coalition military operations. And our sponsors are the US Army Research Laboratory and the Defence and Scientific Research Laboratory in the UK. And the project's been running for just over 2 years. And the goal is to work towards a future architecture that we've described as a distributed federated brain. And the reason for that will become a little bit clearer as I go through the presentation this evening. So we have teams from the UK and the US. You can see on the left-hand side the universities involved, and it's led by IBM, but we also have British Aerospace and Raytheon BBN as collaborators, along with Airbus. Now, the specific problem that we're addressing or that we're trying to address is how a common methodology can be developed to enable the operation of distributed coalition services to support mission critical data analytics, and specifically data analytics at the tactical edge of the communications networks. And here we've got a plethora of sensors and systems that need to work together in a communications environment that has variable connectivity and where the location of the required services may not actually be known. Now, normally workflow orchestration requires a stable endpoint from which to discover and then connect together the required services. However, in the highly dynamic edge of network scenario that we're dealing with, this is impractical, if not impossible. And consequently, we need a new class of workflow methodology which can operate in a decentralized manner and also in a sort of peer-to-peer manner. And so the question that we asked ourselves was, could we use a a vector symbolic architecture to describe services and data, and to compose and orchestrate service workflows to dynamically satisfy changing mission requirements. So this type of future environment we're envisaging is sometimes referred to as the Internet of Battlefield Things, or IOBT. And so to set the scene, we can look at the sort of civilian equivalent of that, which is the Internet of Things. And there's various tooling that is used to support the Internet of Things so that you can rapidly design and deploy service workflows in an IoT environment, which brings us to this whole area that we call Node-RED. So for those of you not familiar, Node-RED is a programming tool for the Internet of Things. It is used to enable you to wire together hardware devices, APIs, and online services in new and interesting ways. And it provides a browser-based editor that makes it easy to wire together workflows using a range of nodes that are there in a palette. You can see that on the side here of the Node-RED interface. And you can use the palette to develop workflows, and then with a single click, you can deploy those workflows. The challenge, however, is that when you actually look at the Internet of Things, whilst the general impression is the Internet of Things are devices that are all connected together, in reality, it's a centralized architecture. And Node-RED operates in this way. It essentially sits, you can think of it sitting in the cloud, and the cloud is connecting out to edge devices that you can see here on the left-hand side. So it is really a central point of control. And what I want to show you this evening is how we can move from that environment of using Node-RED to a Node-RED environment where we can take the workflows, we can map the workflows into a vector representation, a vector symbolic architecture representation, and how we can then deploy that architecture into our wireless network, where the services in the wireless network have been enabled through a layer that I'll describe a little bit later on, to be able to respond to the vectors that are transmitted. And from the vector, we can discover the services that we want to compose our workflow with, and we can connect those services together, all by just comparing vectors. So it's a sort of vector representation scheme that we're dealing with. So the question that might arise then is, why do we want to use hyperdimensional vectors? And in particular, in this case, we're using hyperdimensional binary symbolic vectors. Well, the answer to that question is partly to be found in the desire of the DIAS ITA to work towards the concept of a distributed federated brain. And we were particularly struck early on by the work of Chris Elias-Smith, and particularly his book on how to build a brain, and the ideas in that book about the semantic pointer architecture, where the vectors are pointing to concepts, but the vectors themselves represent the concept that they're pointing to. Now, hyperdimensional binary vectors, by which for the rest of the talk I'm going to mean 10 kilobit binary vectors, have some very useful properties when it comes to describing workflows. If we can describe a service with a single binary vector, then the size of the hyperdimensional vector space means that two services that are not similar will be well separated in the resulting vector space. And additionally, workflows are essentially sequences of service calls. So we can think of the sequence of binding operations that we can perform. We can use this binding operation to construct a single vector that represents a sequence of operations. And of course, using binding and unbinding operations, we can both bind workflows together or sequences of operations together, and we can unbind them. Now, the two types of workflow that I'm sure most of you are familiar with are the cyclic shift binding operation, where we construct a vector by binding together through a majority sum add operation. We bind together vectors A, B, C, E and B and so on, or whatever sequence we want to represent, by performing an operation on each of the vectors. And although that operation could be a random permutation, it turns out, as Penty pointed out very early on, that we can do this with just a cyclic shift, because a cyclic shift of a random vector is equivalent to a random permutation. And so one way of constructing the vectors is to use the cyclic shift operation, and then the unbinding operation is simply to perform the operation in reverse. So we cyclically shift to the right if we want to bind, and then to unbind, we just cyclically shift in the opposite direction. So in our scheme, the power here represents the number of cyclic shift operations in order to construct or deconstruct or unbind the vector. In the same way, we have permutation binding, and we've already had some talks from Ross Gaylor about this, where we have role Fuller pairs, and we combine things together, and again we add them together using a majority sum in order to produce the vector. And the nice thing about the permutation binding is that if we want to unbind, we simply take the role vector or the position vector, XOR it with the vector that we've constructed, and it will expose the vector that we're interested in plus noise. So those are the two basic binding schemes. But the other interesting thing, of course, is how many vectors we combine together. And again, this is well established, and most of you, I don't want to teach you to suck eggs, but most of you know that these binding schemes are equivalent. And the more vectors that we bind together, this is just showing that whether we're using what I've called pi binding or permutation binding or cyclic shift binding or the XOR binding, they're both equivalent, but these are the Hamming distance is here. This is the number of bound vectors. This is just random vectors, and as we bind all vectors together, we get closer and closer to a point where we can't differentiate our bound vector from noise, and at that point we can't unbind anymore. And by setting a threshold, and typically we set a threshold so we have a very low probability of matching with a random vector, a threshold of 0.475 in this particular case gives us an error for a single vector comparison of 1 in 10 to the 9, which tends to give us about 89 vectors that we can bind together. And if we do that, we can unbind all 89 reliably with an error of around 1 in 10 to the 6. So that's the sort of binding that we're doing. So let's have a look at what some of the challenges are. How can we actually describe services as symbolic vectors? Now, if you were to look at standard service representations in something like Node-RED, the service representation will be described in a JSON file. It'll have things like inputs and outputs, the type of input, the type of output. It'll have some sort of description of the service itself, what it's doing. It might have some representation of the resources that the service needs. It may have some requirements in terms of quality of service. And the obvious thing to do, you might think, would be to use the sort of permutation binding, the role filler binding, in order to represent a service. So if we think of our service vector ZX as some role or service vector XORed with our service vector representation, a resource as a role, and a as a role, and some quality of service vector, we might think that would be a good way to represent the service. Of those vectors is in turn a vector itself, because the service description might be in terms of inputs. So again, we have role filler pairs for inputs, the name of the service, some description of the service, some output requirements, and similarly for quality of service and resource. And of course, these vectors themselves might be vectors of vectors that we want to bind together. Now, although that might be, the sort of obvious way to do it, there are some real challenges in doing it that way. And I'm not going to go into too much detail about this, but just with some simple examples, you can see that there are challenges of doing the permutation binding, where if you're binding together services using the permutation operators, and you're using similar permutation operators for different services with different fillers, then just by combining services together, for example, you can end up incorrectly exposing, say, in this case, vector A, when you didn't realize that that was what you were doing when you combined the two services. And similarly, if you unbind the first part of a service vector S1 using P1, you can end up exposing a vector representation of another service, A, Y, for example. So you're incorrectly exposing the wrong vector. And what we're trying to do is to represent services with these vectors and then use the vectors to discover the services. So services describe themselves as a vector, and then when we want to discover those vectors, we're going to transmit the vector incorporated to a workflow, which I'll come on to. But we want to be able to describe the services so that with the vector, if their vector matches the vector in the request, then they know that they're a candidate to participate in the workflow. So this type of challenge is a problem for us. And of course, we get similar challenges if we do cyclic shift binding, because we may have subsequences within our service representation. And here we're just using simple words to illustrate this. But of course, you can end up getting matches on combinations of other services that are undesirable. So our solution to that is to come up with what we call a hierarchical hybrid binding scheme that uses both the cyclic shift and the permutation operators together with a stop vector. So here's the sort of equation that describes what we're doing. And if you just write that out in full, you can see that the vector is described in terms of a position operator, in this case, with our service Z1, then the position operator XORed with another position operator XORed with Z2, but Z2 shifted by 2. So here's the cyclic shift, here's the permutation, and we add them together using majority sum together with this thing called a stop vector. Now, here's basically what we're doing. We're starting off here with service Z1. We're using the binding operation to bind it together into the vector ZX. And we can continue then to bind, we could take more vectors down here, bind them into a vector for say Z service 1 or Z service 2. And by binding those vectors together, we create another layer of vectors, and those vectors themselves can be bound together using exactly the same scheme, where the P0 operators are used again at this level. So we've got different levels of hierarchy, and you can think of these levels of abstraction, where this vector represents all of these vectors, and the vector at the top level represents everything below it. So that's the general idea. There's a lot more detail on the slide, and you can ask questions later if you want to know how all this works. Now, the thing is that if we want to unbind that vector, then if we take our ZX vector here, in order to start a workflow, we're starting from this point here, we would actually construct a vector Z1 prime, where we take our P0 operator and we XOR it with the vector ZX, a clean version of ZX. We add in this vector called T, which we need in order to be able to locate where we are within the service. And so we now take this vector, we cyclically shift by -1 in the left direction. And what we end up with when we transmit that vector, first of all, is Z1 exposed plus noise. And so Z1 now sees that vector, and because Z1 knows about itself, knows its vector, it knows that it's a match. When it receives that vector, if we want to now move on to the next service. This is our sort of, oops, sorry, this is our chains of services. If we want to move to the next vector, we want to transverse horizontally. And so again, we perform this operation here, and the next vector is then exposed, Z2. So the idea is we can move down through the hierarchy and we can move across the hierarchy. And I'll show you how that works in a moment, but we also want to demonstrate that this is extremely scalable. And by scalable, what we thought we would do is actually demonstrate the binding scheme by creating a vector that completely represents the whole of Shakespeare's play Hamlet, where we treat the actors as services, and the actors have the role of playing their part at the appropriate time in the play. So if you look at Hamlet, Hamlet's got something like 30,000 words in the play, and 4,620 unique words, and we've got all the different actors. And if you think of this as a sort of complex workflow with all the actors interacting together, that was the idea behind using this as an example. And of course, you can look at scenes and acts, and you can see different types of interaction that are going on. We want to be able to demonstrate how the binding and unbinding scheme works. So in order to do that, what we actually do is we start off by creating just random vectors for an alphabet. So we have the letters of the alphabet and capital letters. We also have some punctuation and so on as vectors. So we don't need that many vectors to start with, and we need enough position vectors to allow us to build up a vector of a particular chunk size. So what we do in the scheme is we take the letter vectors, we bind them together to create the word vectors. And then for each stanza that an actor speaks, so if you're familiar with Hamlet, the very first stanza is by Bernardo, who says, "Who's there?" And then Horatio says, "Nay, answer me, stand," and so on. So what we're doing is we're first of all constructing the stanzas. The stanzas in a particular scene are bound together, and then all the scenes are bound together into acts, and the acts are bound together into the Hamlet vector. So right at the bottom, we have vectors that represent each of the words, and at the top level, we have a vector that represents the acts. And when we want to unbind this particular scheme, what we can do is we start with the Hamlet vector. We take this Hamlet vector, we unbind it once and transmit it, and when we do that, we expose A1. Now, A1, A2, A5, and A1, S1, and so on in this representation are, you can think of as a distributed cleanup memory. We need a clean version of the vector because the vector that A1 sees is A1 plus noise. So A1 actually has a clean version of itself. So when it receives the vector, the first thing that it does, or the only thing that it needs to do, is unbind the vector, and it retransmits the vector. And the vector then exposes A1, Act 1, Scene 1. And again, the same thing happens. Act 1, Scene 1 unbinds the vector, and it exposes actually stanza 1 for Bernardo. And in fact, I'm not going into all the detail, but that can be broken down to the individual words of stanza 1. And in fact, if you want to, the individual letters of each of the words. But at this level, what we're doing is we're representing each of the actors as holding a number of the stanzas as vectors. So what now happens is in our play, we now distribute the actors across a wireless network. And we've actually done this with an emulation of a wireless network. So the actors now sit on different nodes in the wireless network, and we inject the Hamlet vector into the network. And also in the network, we have the distributed cleanup memory with Act 1, Scene 1, and so on. And so as the play progresses, each of the actors says their particular part in response to the vector, unbind the vector, pass the vector on, and the next actor says their part. And the whole play plays out in this distributed setting in exactly the way that I've shown you. And one of the other things that happens is if during the play, and in Hamlet, nearly everybody dies, so at some point we lose connection in our network with Hamlet and he dies, then Hamlet's ghost appears somewhere else because we have multiple copies of the same service. And so another Hamlet appears and carries on and performs the rest of the play. So another interesting thing that we've shown is that with these vector representations, that the hierarchical binding actually gives you a representation that in some sense semantically or at least syntactically represents the play. And to demonstrate that, what we're showing here is the Hamming distance at different levels in the hierarchy when we compare different versions of Hamlet. So we have two Old English versions of Hamlet, and we have an Old English version and a New English version of Hamlet. And what you can see is that above our 0.47 threshold, we can quite clearly see that at the whole play level, we're above the threshold for the Old English compared with the other Old English and the Old and New English. And the same thing occurs at Act 1. We have a bit of a problem in Act 2, but all the other acts are easily comparable. And in the same way, we have Macbeth as a control, and you can see that Macbeth is completely different from Hamlet. And that's reflected at every level in the hierarchy. So we can do these comparisons to be able to see that there are these differences. So that's all very well with something like Hamlet, but how do you do this for complex workflows where this is not just a sort of linear sequence that's followed through, but we have a sequence of services that are linked together in quite complex ways, where not only do you need the services, but say this yellow service here has to connect to a particular green service, and another link has to go through a particular blue service, a red service, and so on, and back to the same service. So you have to capture both the nodes that you need and the connections. And this is where Node-RED comes in. We can represent this workflow in Node-RED. Node-RED produces for us a JSON or an XML representation of the services and the workflow. And we use our binding scheme to create these vectors that allow us to transmit a vector through our network and pass it between the services. And just to illustrate that, this is essentially what we're doing. In this case, our workflow vector has two components, a recruit nodes vector and a connect nodes vector. And again, we have this start vector here. And in the recruitment phase, so that's the first thing that happens as we start to unbind the vector, we're going to gather the nodes together. And then in the second part of the phase, we're going to connect the nodes through parent-child relationships that are represented in the JSON. We're going to use a vector representation to do that. And so essentially what happens is you can think of your services as sort of distributed around your wireless network. And what happens is we launch the workflow vector, just a single vector. And one of the nice things about 10 kilobit vectors is they fit neatly into a single wireless packet. We transmit that one vector, and you remember the first thing the vector's going to look like is a yellow node or a yellow service. And a yellow service responds. And we use some techniques that you need to read the papers about for how we guarantee that only one service is accepted. But when that service receives the vector, the control is passed to that service, and that service unbinds the vector and just retransmits it. And when it retransmits, it finds the next yellow vector. Service control is passed to that node, and it finds the next vector, and so on, until we've got the yellow nodes, and then we gather the blue nodes, and eventually we collect all the nodes together that we need. And at that point, when we unbind the vector, it tells the first yellow node which blue nodes to connect to and which green node to connect to. And the whole process continues just by unbinding the vector multiple times until we get the complete workflow. And we can do this for all sorts of workflows. And I've nearly finished, Evgeny, so I'm just about there. Okay. So we can do this for all sorts of different types of workflows. And if you want to know more details about how all this works in detail, I've put some useful references here for the papers that go into all the details of how all this processing works, and in particular, how this layer that sits on top of the services has to operate to handle the vectors in terms of listening for them, receiving them, recognizing that they're the same service, being accepted, unbinding the vector and retransmitting. So just in conclusion, we've shown how these services can be represented as bound hyperdimensional vectors in a binary vector space, how the service workflows can be represented. We've demonstrated how workflow composition can be performed in a fully decentralized wireless network environment, just through a simple mechanism involving the exchange of these binary vectors. And we've demonstrated that IoT workflow tools like Node-RED can be extended to construct these vectors automatically, and then we use them. And what we're currently doing is investigating how to extend the binary symbolic vectors to cover cases where we have completely different words and symbols used by different coalition partners. So we're using semantic vector representations rather than sort of random vectors built up from an alphabet. And we're also investigating how to construct semantic vector spaces for services that capture the interface and the function of the service into a single bound vector. And then finally, I think what I want to say is that this type of symbolic vector representation that we've described will make a significant contribution towards the future vision of an Internet of Battlefield Things as a distributed federated brain. So I'll finish there.
All right, Graham, thank you very much for this exciting talk. Sorry, I was about to interrupt you, but I was hesitating until the very last moment. Still, we are a little bit late, but I cannot stop myself, and I would like to allow a couple of minutes for questions if there are any. So please unmute yourself if you have any questions.
How big is the cleanup memory for Hamlet?
Right, so the cleanup memory essentially consists of cleanup memory just for each of the scenes. So there are 5 scenes, and then for each of the acts. I can't remember exactly how many acts there are, but that's it. That's the only cleanup memory we use for the whole of Hamlet.
Okay, so it doesn't go down to the granularity of like triples of words.
No, we didn't need to, because we have enough capacity in the vectors to be able to handle quite large chunk sizes.
Okay.
Yeah, we did run 2 versions. On one version, we ran it so that we had sentences also as cleanup vectors, just in order to look at the scale. But because it's distributed, remember that the memory consumption is also distributed, which helps us not to have a massive load of memory on a single edge device.
Okay. Last question. All right. Well, if you think about any extra questions for the current talk, please use email, our email list, or write your correspondence directly to the presenter. I would definitely encourage you to use our mailing list so that we keep it alive as a live tool for discussions. So